Before I go on, I wanted to go back and just emphasize a few things about collision theory and standard heats, which I had mentioned actually in the previous video, before I jump ahead to bond energies and Hess's law, which are the next two sections I'd like to cover a little bit. First of all, a couple things just to recognize. The reaction process isn't always a single step reaction. Sometimes reactions have multiple steps, so it may be something like A produces B. Actually, let me make that line a little bit thicker. It's easier to read if I do that. And then maybe B turns into C and C turns into D. But when we're looking at the overall reaction, we're really, we talk about, well, A goes through and turns into D. And you don't think about all these steps along the way. And basically this is a sequential reaction. Multi-step reactions like this sometimes will go at different rates. Not all these reactions will be at the same speed. So this one may be extremely fast, and this one may be extremely fast. But if this one is extremely slow, this then controls the reaction. So first thing I want you to just recognize is some reactions, many reactions actually, are multi-step. And whatever the slow step is kind of will govern the rate of the reaction. Now, in talking about rates, there are a couple of things I want to mention. I mentioned this in the last video, collision theory. Collision theory kind of discusses a little of this, and basically collision theory describes the conditions required for effective collision of reactants to produce a product. Basically, it says that you have to have a minimum amount of energy, and you must have the correct orientation. Now, if you're dealing with two simplest thing would be like, maybe two atoms. All they need to do is collide. The orientation doesn't matter as much. If you have something that's rather complex, maybe a large protein or something like this, and to react, the other thing that reacts has to fit, and that's not necessarily a great drawing, but pretend this fits right in here. Well, these things have to collide in exactly the right orientation for this reaction to occur. So, simple thing where you maybe have just two, basically, round atoms colliding is very different than something like this, a very large molecule that's kind of complex. But both are going to require a minimum amount of energy. This one is going to require specific orientation, and this one is a little bit more general. But depending on how many of these factors are involved really will affect the reaction rate and how quickly it will go. So what's happening is these reactants come together, and as I mentioned in the last video, they're going to form an activated complex, which is basically a transition structure. And a way to look at this, and in the previous video also, I did these diagrams where I maybe had reactants and products, and I said that what would happen is here's my activated complex, and to get here I need a minimum amount of energy, which I called the activation energy, or E sub A. It's almost analogous if you look at it. If you've got pretend you're playing mini golf and you're standing here and you're putting, and again, I'm not an artist, but pretend that's a golf club, and there's your golf ball, and the hole is over here. So here are my products, and here's the hole that I'm trying to get it into, but along the way there's this hill that I have to get to, and we've all done these crazy mini golf things. Well, what's going to happen is if you don't hit the ball with enough energy, it may only go part way up the hill and then come right back, part way, come back. It needs to hit this hill with enough energy to get to the top. If you give it just enough to get to the top, at the top it might fall back, it might go this way. But the fact of the matter is, for you to get to the hole, or going back to my analogy for you to get to the products, you need to have the minimum amount of energy, or what I've been calling the activation energy, for this to occur. Now, chemical kinetics then is the study of all this. It's the study of reaction rates, reaction mechanisms, and so forth. And of course, that rate, the reaction rate, is going to depend on several things, and I've mentioned in previous video. Things like collisions, basically. The more collisions and the greater the force of those collisions, the more likely it is that you're going to get your product. Things like, the nature of the reactants. Is this a fairly simple reaction? Is it a very complex multi-step reaction? Can come into play here. The amount of surface area. If you have two things coming together and you have a lot of surface area, there's a greater likelihood that you're going to get an effective collision because you have more chances from that greater surface. Things like temperature. If you increase the temperature, you're going to have more collisions, greater force in those collisions. That will speed up reactions. Concentration. Again, the more stuff, the more the more collisions you're going to have. You know, the more people I have running around a room, the more collisions we're going to have, the greater concentration of my reactants, the more collisions I'm going to have. Also, catalysts help this, and I mentioned this in a previous video, but basically what a catalyst is if this is my reaction, my energy diagram, a catalyst is something that will lower this activation energy. Typically, it provides an alternate mechanism. In biology, those are typically referred to as enzymes, but a catalyst is the more general term. And so what would happen is you would have something like this. You would have a lower activation energy hill because you're having an alternate pathway that generally needs less energy for this to occur. So what ends up happening is the minute I lower this, more collisions. If I have a whole bunch of collisions, more of them will have this amount of energy than will have this amount of energy, and so therefore my reaction will speed up through the addition of that. Okay, so that's a little bit on this collision theory, how these things work, and some ideas on that. The other thing I want to mention very briefly is the whole idea of standard heats, heats of formation, and so forth. As we've been doing equations, you'll end up with equations like this, and these are both exothermic reactions. Notice they both have a delta H notation. It's negative, so that means these are releasing energy. And as you look at these things, I want you to recognize a couple of things. This one is, well, let's do this one, I guess. 4 moles of ammonia will react with 5 moles of oxygen to produce 4 moles of nitrogen monoxide and 6 moles of water. The heat change for this reaction is negative 1170. Now recognize a couple of things. If I said to you, how much would this be for just 1 mole of water? I don't want to produce 6 moles of water. Well, what can I do? Basically, you would divide everything in here by 6. So this becomes, of course, 2/3. This would be 5/6. I'm sorry, 5/6. This would be again 4/6, which of course reduces to 2/3. This divided by 6, of course, gives me the 1. So then guess what I do here? Again, I'm going to divide that by 6. So recognize that as I work with these equations, these heats of formation or these enthalpies of the reaction, the amounts that I compute these with or report these with, if I want to change them, I can do so by doubling, tripling, dividing by 6, whatever I want to do the equation. As long as I do that to the heat change, the enthalpy change, it all works, and you can do that sort of thing. So just recognize by multiplying or dividing, as we work with these equations, you can do that, but whatever you do, just do to the heat change as well. Now, what I want to mention here is what's called the heat of formation. The heat of formation is the energy released or absorbed as heat when 1 mole of any compound is formed by the combination of its elements. And I have an example of that here for liquid water. The elements are coming together to form 1 mole of water. Now notice this is always reported, or it's generally reported per mole if you're dealing with the heat of formation, and you're forming it again from its constituent elements as they're coming together. So what ends up happening is these are in what we call their standard state, which is their state at normal conditions. Normal conditions in thermochemistry are generally 25 degrees C, 25 degrees C, which of course is 298 Kelvin, or 1 ATM, which again is 760 millimeters of mercury, 760 torr, 101.325 kPas, and so forth. So, but under those conditions, when you bring hydrogen and oxygen gases together to produce water, which would come off as a gas and then reduce it down to liquid, this is the amount of energy that would be released. So this would be what we'd call the standard heat of formation. So a lot of times you'll see that denoted as this. They'll do the enthalpy change or standard heat. F, or usually it's a lowercase f, indicates the heat of formation, and if it's done at the standard state, they'll put a little, looks like a degree symbol up here. And again, that means it's done at these conditions, the standard conditions of producing these sorts of things. Let me redo that line. My tablet here, I drifted down there. So again, these are the standard conditions, and if I'm reporting this at those standard conditions, I put the little delta H with the degree symbol in the upper right. Now, elements in their standard state, somebody might say, well, what's the heat of formation of these guys? It's always defined as 0 because they are already in their elemental state, so we consider those to be 0. So if you're ever asking, what's the standard heat of formation for an element, nitrogen or argon or anything like that. Now, what I can do now is add these equations together to predict the enthalpy change for reactions where I have not even done the reaction. And that's called Hess's law. I'm going to show you that in the next video. But as I work with Hess's law, I'm going to be using these sorts of equations, these heats of formation, standard heats of formation, and I'm going to be adding them and working with them so that I can predict unknown reactions. So I'll show you that in the next video.